Okay, well, good morning, folks. It's good to see you all. I look forward to sharing some more interesting information on our course today. And let me, as I typically do, go ahead and open this up in prayer, and I'll give you a sense of what we're going to be talking about today. So, dear Heavenly Father, Lord, thank you for the chance to work with each of the students in this course, Lord. I pray that all the material that we cover will be clear, that these will be things that are going to be useful for them to understand better what it means to be an engineer, and for this course to get a chance to, as if you were having on-the-job training of what it would be like to be a systems engineer. In terms of their spiritual formation, Lord, I pray that you would be working with each of the students and helping them to understand the scriptural concept that they're learning as they're studying the Bible, give them the insight to be pulling out the theological concepts that we want to be inferring from that, and to be able to apply it in the various situations we face in our lives, and give them interesting ways for faith integration. In Jesus' precious name we pray. Amen. Okay, well, we're going to continue in our journey through our main textbooks, System Engineering Principles and Practice. And so where we're at right now, we're slowly getting through this concept development phase. And you can see that for a systems engineer, there's just judging by the number of the chapters, that there's a lot of things that are going on for a system engineer in the beginning part of a program. And that can be very intentional. That the phrase you've heard me several times say is system engineering is like insurance. You buy as much as you can afford. And so you want to be helping to figure out what is you're going to be building based on what the stakeholders, the people that want to employ you to be doing this, to make sure that you're capturing exactly what they are doing. We're also going to be tying this in to a couple different areas in terms of our SysML development. And I will be spending some time talking about block definition diagrams, because that's the next one that's due. And so with visual paradigms, I'll be opening up that, and also the other tool that I've been using that you've seen me talk about. So we'll go over that. Well, for this chapter, we're going to be talking about evaluation and selection. And so let me just give some context there. I've also added some material beyond what I had in the lecture notes that I posted in Canvas, as I continue each week trying to add a little bit more information that might be good for contextual reasons, that you'll get a better hands-on experience of this. So we're going to be looking at evaluating and selecting the system concept. And so we want to have enough details about that so we can be exploring that. And so objectives of the evaluation phase are to analyze a range of options that were developed in the previous chapter. So we talked about that on Tuesday when a system concept was under development. So as we move along, we get more precision in terms of what exactly we're talking about. So we want to refine not only a system concept, but having what we think would be the best system concept that we would want to go forward. So decision makers will be cognizant of system performance as well as development schedule and cost when making decisions regarding the concept to advance to design. So that's what we're doing. We're in the concept design. We haven't actually started to build things yet. We're analyzing it to see how well it seems like it's going to work. And so the previous textbook that I used up to this year, I flipped to what was the major textbook, and it talked about a little bit clear, talking about going through this process from requirements to functional architecture to physical architecture. And this is tracing a lot of what we're doing in this course. Is we have the use case diagrams to get a way of how to communicate what exactly we're doing. From that, we can be deriving requirements. And then we gradually get more specific, first having those functions, and then gradually get into more physical specific items. And so I've been trying to give some perspective on that. And I have a handful of slides that will be going over some Freudenthal material to help us to see that. And so the physical architecture of a system is a hierarchical description of the resources that comprise the system. So this hierarchy begins with the system and the system's top level components and progress down to the configuration items that comprise each immediate component. These configuration items can be hardware or software elements or combination of the hardware and software, people, facilities, procedures, and documents. And with the context of what I'm trying to tie in with our SysML development, I'm going to try and tie that into a block definition diagram. But these next handful of charts are also going to be talking about another related item, and that's this package diagram. So package is where we start to show encapsulation in a certain way. So from chapter 6 in Freudenthal, they talk about the package diagrams. And so this is the idea, the system that we've been talking about from Freudenthal. There's this surveillance system where you have 24/7 observation, trying to make sure that you see the bad guys and detect them and prevent them from having access. So a top level package is a model shows packages at the next level of the model hierarchy. And so that's what we're seeing here. And so very, very high level for a surveillance system. And so now we're just trying to show, okay, we're going to be having some standardized components we're going to be using, say from a model library, we're going to have standardized definitions. And so we'll have like cameras, recording devices, and we're going to be coming up using some standardized product lines and having a profile in which they're going to be leveraged. And so packages are often contain subpackages that partition model elements into logical grouping. A well-defined model organization is important as model elements increase. And so you'll see this on the next chart in a second. Figure 6.3 from Freudenthal shows a nested packaging structure by contrasting a structure with a similar flattened model in 6.4. So large models can become difficult to manage if not partitioned into subpackages. So this is now getting a little bit more detail. So we have a surveillance system, and we're going to be then starting to flesh out the next level of details. We have to be doing analysis, physical architecture, logical architecture, use cases. We've been starting to do this with each one of you with the projects that you've been working on. And so the surveillance system package hierarchy is organized based on architectural principles that require logical architecture, a physical architecture, use case packages. It also contains analysis packages from various kinds of analyses and their outcomes. So I was encouraging folks to have, say, like 3 use case diagrams. You can have a variety of them that would be necessary to capture everything. You're going to analyze how each one of those is going to perform. Outcomes with first having a logical or functional architecture working into the physical architecture. And then we could start to see how things are related. We can have layers of things that start to pop up. A little bit more details here. So this is a flattened approach. So we're showing the same things, but say for certain audiences, we don't need to be getting in all to the details here that we've been showing. And that could be another possible way of considering how that would work. And so I'll focus on package diagrams next Thursday, because that's going to be the next thing after what we're doing here. And so you can also have a model package organization, and you've been seeing this both in visual paradigms as well as the Cameo system modeler. It has multiple names, but I'll just use that, and you'll see that in a little while. And you can see how things are laid out. And so the products, you can have the cameras, the requirements, the surveillance network, the surveillance system. All of those things have to be fleshed out. You can have different profiles and how it's going to be performing. And this was something I found on the internet just to give you just a fairly pretty involved surveillance system of having all the different kind of cameras and trying to assimilate all this information to be detecting the bad guys and making sure that you have physical protection is, say, one of the drivers that could be coming up for that kind of capability. An important thing that actually is done in system engineering is called an analysis of alternatives. And the things that is part of that is you're analyzing each of those alternatives. And so let's start out with that. And I'm going to have a couple slides that'll be talking about the James Webb Space Telescope as well as Hubble, giving some comparison that might give you a sense for you with the trades that you're going to be doing with your projects that each one of you is been working on. So the full alternative space should be considered when evaluating the design to satisfy the functional architecture developed in Chapter 7. After the functions for the system concepts have been defined and validated, the system engineer should then consider how the design may be developed in order to effectively execute the functions. So we're going to that next level. We're doing a day in the life of how that works. We're seeing how things are all going to come together. Evaluating all possible combinations of designs may provide a starting point and eventually provide the decision makers with a limited number of feasible system concepts to progress to design. So you can see there's a slow down select. And so maybe you have a dozen, maybe 2 dozen possible types of architectures and system concepts. We need to start to flesh that out to see how feasible they are. And so you want to be thinking about alternative implementation concepts. What would be the best way of starting to go about doing that implementation? Yeah, like for Abby doing her electric vehicles, like one of the key components for an electric car is the batteries. And so that was a key driver. And so Tesla created new batteries. Um, with some of my light level research in that area, there are other manufacturers, Japan, I think it's Hitachi or Toyota or Honda. One of those is actually developing some other technologies that would be used for batteries that could be yet even more efficient for storage. What is the technology development? Maybe you have an idea, it's there, but it's not quite at the technology level that's needed. And so that could be part of your design and part of your life cycle process that needs to be developed. And then we get into this performance characteristics. We need to have the next level of requirements. And so we start with doing some characterization of that to get some perspective. So I think probably most of you have heard of Hubble, and maybe by now you've heard of the James Webb's Space Telescope. And so just doing some research, going to their website, it says that the James Webb Space Telescope is a giant leap forward in our quest to understand the universe and our origins. So this gets into the science mission. Webb is examining every phase of cosmic history from the first luminous glows after the Big Bang to the formation of galaxies, stars, and planets to the evolution of our solar system. So that's a lot of things here. But on that same web page, this is on the bottom, it's specified 4 of these major initiatives that they're trying to do. So look at the early universe and the hypothesis, and some wouldn't agree with this hypothesis, but I'm just going to go with it for now, is that if you look from one part of the galaxy to another part of the galaxy, the light has taken so long to get from point A to point B, so you have, in a sense, the ability to look back in time. So that's the presupposition that's based on this early universe trying to characterize. We have this um, trying to look at galaxies over time. So if we look at galaxies that are close to us, didn't take us long to get here, so that will be something that's closer. Looking at something that's farther away, so maybe not the early universe, but something a little bit later. We can be looking at star life cycle. So just taking the full gambit of all the possible places you can look in the heavens, you can see one that say it's a very old galaxy, one that's a relatively new, and some of this observation are things that have been done by Hubble. And finally, looking for exoplanets. What are places where you could find stars that have orbiting um, planets that we would like to be seen? Are we alone in the universe? And those are some of the things that Hubble and James Webb are trying to work at. And so this kind of gives you a sense of like, well, what would be the requirement space? And so then if we wanted to start to do an analysis of alternative, typically an analysis of alternative, when you get to that level of investigation, you would have 3 to 5, maybe even more than that. But this was a chart that I found that just was doing a comparison between the Hubble Space Telescope and the James Webb Space Telescope. And so maybe this might be a way of how you can be considering the information you've developed so far, that you can be continuing in on this development of your project. So you have like, what is the optical mirror that they have in meters? And so there's a 2.4 meter mirror that's used for the Hubble, and it's mostly in the optical regime. The James Webb Space Telescope is actually not a circular aperture, and so it's not a diameter, and so it has a little bit longer length going up and down versus east and west, and so it is 6.1 by 6.6 meters. So the James Webb Space Telescope is actually weighs less. And so this is circling around the Earth. This is in a very interesting orbit. It's called a Lagrange point. And so, but those are some characteristics. The power, roughly maybe on the same order of magnitude, a little bit less for the James Webb. So I'll just mention a couple of things here. So you could just see what is the one of the key elements in a imaging system is something called a pixel. Maybe you've heard that term when you buy a new phone or you're buying a camera, it'll say how many megapixels are associated with that camera. Well, we can see here that for Hubble, it had a 25 megapixels available in its detector array, while for the James Webb, it's more than twice than that. And then the volume per day, it's just gone up by an order of magnitude, like 20 times more is being produced by the James Webb as compared to Hubble. So these are just some things that you could start to be observing, some characteristics, and say the cost of this is 1x and this is 10x. And so cost is an independent variable. Maybe it might be saying that, well, maybe we should just go with a Hubble option. But if there's more specific requirements that are drivers that you have to do, you may end up having to go with the James Webb. And so that's what you start to be doing with an assessment when you're doing an analysis of alternatives. So there's something called operations research. And so you're trying to see how things actually work, how they operate. And so the system engineer may perform some analysis on the problem in order to calculate the best performance and cost combination when considering the full alternative space. And so these techniques seek to minimize or maximize the objective function, and the decision analysis techniques can help to visualize the decision space possibilities when determining the best solution to pursue. These are some charts that are in the textbook that you can be seeing. And so here we can see that we have 6 alternatives. I was just showing here, just for simplicity, what I was able to generate with some real data, looking at 2. But here we have 6 examples, and one are, say, a single role system. And then we have 3 that are actually multiple role. And so these are multi-missions, these are single missions. And we can be starting to see how things are laid out in different functions. Not all of them can do these functions. And so we see the ones that have a 1, that means that they can do it. And if there's a 0, it can't. And so say we can see that there's more systems that can do function number 1. We can start to see, look at it in this direction. We can see 1, 2, 3, 4, 5. This multi-role system, we can do 5. The single role system, it can only do 2. And so these are some helpful things for us to help to be figuring out, well, which one should we go forward to actually develop. And so there's a lot of things that need to be considered. And so system engineers, that's another characteristic. They have to be handling a lot of different types of details to make a decision. Here is something called a decision tree, where you could be starting to figure out, well, which is the best solution that we might want to be going forward. And the textbook walks through this in more detail. I'm going to kind of go over this in a light fashion. This first one is just giving just the probabilities associated with how things would go from one to another. And so you have that. And so which would be the best option? And so you can actually, with this decision tree, you could start to actually figure out which is the one that actually gives the best value across the board. And so you start to work your way down that tree. 42 is higher than 37. We still see here that we have a couple possibilities. And so we have the 70 that's greater than 40 and 30. We can continue to progress along that way as one possible way of considering what we're going to do. So maybe we go with this top option. Um, and so this is just yet another thing that could be helpful for us to have a analytical tool that can consistently come up with these results. And so we have a way of, in an unbiased sense, that once you figured out all these weighting schemes, you can be figuring out, well, which is the best option. So that's one possibility. You also kind of in economics and affordability, the system engineer should be cognizant of affordability assessments, which may help decision makers understand the resource allocations, helping to quantify stakeholders' expectations, and helping to deliver portfolio outcomes that stay within budget estimates. So like what I was just saying for this comparison, if this is 10 times more expensive than Hubble, and this is the performance really that all I need, then maybe this is the best option. I may not always go with the most elaborate type of capability, and ultimately it depends on what is most important to you. Elements of affordability to be considered at this stage of system development include cost estimation and analysis, investment decision analysis, and resource efficiencies. There's also cost estimating and analysis, trying to come up with some basis of estimate. And even when you were doing your proposals, you were having to think of cost, what would be the total um, hours that would be required to do a system. You were beginning to think about some of these other things. There's also the investment decision analysis. And so how much is reasonable to invest to say to me maturing the technology so that we can actually say get the James Webb Space Telescope, because there was a lot of things that had to happen. You're at a distance where you can't go service this. This is still within reason. It was easy for the space shuttle to do, for us to actually do servicing mission, and they actually did life extensions of the Hubble. James Webb, that's not going to be possible. So that means that there's going to be some more investments that's going to be required because it's going to be at a far, far away place that we want it to operate for a long time. And then think about what are the resources efficiencies. That's another area that would be thought about. There can be some other benefits that need to be considered. Safety, suitability, performance. Safety is one of those things. Say if you have like a manned mission to Mars or even a manned mission to the moon, this is another thing. We have to be thinking of safety of life considerations. And so that could impact how you're going to be doing your system. The human factors, even though you may have two systems that both do the functions, one may be a lot easier to use. And so human factors is going to be important. Supportability, you have something that's actually deployed. How do you maintain it? That's going to be important. And so how much time does it require to be doing different things? And so it gives an example of the time spent mowing the lawn, maybe doing a retrofit of a missile silo, thinking in terms of what Nathaniel was doing with his project, just to give another example. And then when you actually get done with some of these things, you can have these scatter plots where you can start to do an evaluation of different types of alternatives. And so here we're trying to emphasize what is the amount that is saved, how many benefits, and so you could say that something up in this upper right quadrant would be something that would be really good. And so, say this system here, it doesn't have as many benefits, but it's saving another $100 million versus this one, and like $150 million above these two options. So thus, if cost is an independent variable for your stakeholders, that might be something that they would want to be thinking about. So this is something called a cost context diagram. You can look in the textbooks for more details. And so this is for a healthcare application. And so system engineering can be done, applied to healthcare as well. And so how do you start to characterize these various things? So fee for service, what is the best way that you can be doing it? What is the the um, the users of that healthcare and the providers of that healthcare, how can they monetize this in such a way that would be realizable and maintainable? um, Advanced technology. If you had technology that all of a sudden it's going to give an order of magnitude better detection of some type of pathology, you're going to be using that, but there's going to be a cost in the near term, but long term it could actually be saving you money. So they'll just give you some examples of how these kind of things can actually be helpful. Even this block diagram to give you all of these things. You could be using this as a checklist to make sure that you considered all of these various types of things that are come into play. So events and decisions for consideration. Some of the decisions that are made throughout the system engineering lifecycle will affect how the system will maintain its schedule for development and operation in the intended environment. System engineers should understand the decisions that are made during the system development and will affect the remainder of the project. And so there's a lot of events, there's a lot of milestones, and having the decision maker saying yes, go forward, or no, you need to fix this. This is going to be something that a system engineer is going to have to be part of. And in this part of the concept development, we're getting a chance to see some of those things. So I'm not going to go through this list, but here are example system decision questions that can be coming up. Does the system satisfy the requirements? That's really important. And that's one of the things that a system engineer needs to be constantly monitoring as the system progresses. There's more detailed requirements. And then you have to be thinking about the allocation, and then you have to aggregate those together to see if they meet a higher level requirement. Does the system address the users that will interact with the system? The operators, is this something that the operators are going to be easily able to use? Does it fit within the concept of operation that they have established? Well, there's a lot more there, but I'm just going to skip over that for now. So we've introduced this to a degree, the alternative concept development and concept selection. And so in the beginning, you have just I like to say like the laws of physics don't apply in the beginning, just to have a brainstorming session to come up with these ideas. And then you get more realistic. System engineers will compile all of the work to present to the decision makers regarding the different alternatives that have emerged through analysis, prototyping, initial concept design. System concepts are evaluated in terms of operational performance and compatibility, program cost and schedule, and risk to achieve each of these things above. So performance, cost, and risk, those are the things that are important. Program risk can be considered to consist of a combination of two factors: likelihood that the system will fail to achieve its objectives, and the impact of the failure on the success of the program. So we're going to have another lecture that talks about risk analysis, and so we'll just leave that for now. And then we get into the formulation of the alternative concepts, modeling of the alternatives, and then we can be better equipped to figure out which one is actually the better concept. So program risk can result in a number of sources: unproven technology, difficult performance requirements, severe environments, inadequate funding or staff, unduly short schedule, and a trade-off analysis is um, fundamental in all systematics decision making, and so you want to make sure that you make time available for that. And so this is going to boil down to what is your selection strategy, and so how do you weight the key performance parameters? How do you engage with the stakeholders so they are constantly having a chance to make sure that they have an input for what you're doing? And then you get into the concept validation. So we've defined them. Now we have a shoot off between them, and a concept selection trade-off analysis should be organized. So it's set up as a distinct process, exhaustive, consider the full range of alternatives. So each one has to be has its test drive. It needs to be semi-quantitative. It uses relative weighting of criteria. So we're not talking about exact dollars. We're trying to show relative merit and say that, overall with these criteria, this alternative performs better than others. It needs to be comprehensive. You consider all the major characteristics, and it's documented. You describe the results fully. And so this is one of those deliverables that would show up that you can say that here early on, we've had this amount of detail to flesh out which we think is the best one to go forward with. And the customer would approve that. So the justification for the development of the selected concept, or maybe you're still going to maintain a couple of concepts for the time being. You show the validity of the need to be met. You state the reasons for selecting the concept. You describe the program risk. You give evidence of the detailed plans using things like the work breakdown structure, the system engineering master plan, and so on. We talked about that at a high level with our introductory lectures. We give evidence of previous experience and successes. We present life cycle costing and cover other relevant issues such as environmental impacts. All of those are things that need to be considered. And then just finishing up with one last slide before we do our summary. So we have a couple possibilities. We can either do traditional, which is this rigorous process that we're talking about, or you can have more of an agile approach. And so concept evaluation needs attention by the system engineer in order for the concept to be known in a timely manner. In contrast, an agile approach may help by presenting the competitive concepts in a similar manner, sharing views between analysis teams, and effectively performing quantitative evaluation of the leading candidates. And so maybe you develop a little bit, analyze a little bit, develop a little bit, analyze a little bit. And so you're trying to show a little bit more of an agile perspective. And so it kind of depends on the type of a system. Maybe if it's a more focused type of component, maybe that would be fine. You get something that's really complex like a satellite, that's going to be a lot harder to do. So we did a survey overview of this, evaluating and selecting the system concept, looking and considering what is an alternative analysis or an AOA, analysis of alternatives. We brought up the idea that there's operational research techniques that are used, thinking in terms of how it's going to operate. You need to be thinking of the economics and affordability. How much does it cost to build? How much does it cost to operate? What is its total life cycle cost? There's a variety of milestones that have to be considered. And you have this crescendo point for each parts of the development. There needs to be the development of these concepts. And finally, as they get developed, you have a methodology for doing the concept selection. We have to be thinking about how we're going to be doing that validation process, and that needs to be quantified. And there's also these two types of variants of system engineering, either traditional, which is the thing that we're going to be focusing on in this course, versus the agile system engineering, which is a more build a little bit, analyze a little bit, build a little bit, analyze a little bit. So let me stop sharing for that and see if there's any comments or questions on what I shared. Maybe I'll also do this thumbs up. Did you guys track what I was going through there? Okay, I see some thumbs up. That's good. Um, okay, I'm going to do a little bit more discussion on another. Um, this is some resources from Freudenthal, and I'm going to go over this quickly just so that since we're now talking about block definition diagrams, I want to make sure that I give you some perspective on that. And then I'm going to switch over to our tools. And so this will probably maybe take about 10 minutes or so. And I'll try and not take too long so we have time to make sure we spend time in our tools. And so together we can real time be creating a block definition diagram. So here we're talking about modeling blocks and their relationships on a block definition diagram. Tuesday, I talked about a car and how it can be divided into subsystems. That could be one way that you could be using a block definition diagram. It's not the only way, but here is we'll get a chance to be seeing some thoughts here. So blocks are basic structural elements. They provide a unifying concept for describing the structure of an entity. So focus on structure, the system, the hardware, the software, the data, the procedure, the facility, the persons, all of this. And so some tools will actually have this double angle brackets for block being at the top. And then we can have some other things that are below that that start to show some relatedness from other things that you're developing in your SysML modeling. So multiple standard compartments can describe the blocks. So there can be properties, operations, constraints, allocations, requirements that the block satisfies, user-defined compartments. So you'll see this in a few minutes that these blocks can actually get fairly large because there's a lot of relatedness that starts to come up. But let's begin just starting with the basic element of what a block is. And so from Freudenthal, here's is an example of a car. Now we're starting to show the structure of an automobile. So we have the automobile. You can see it's labeled block. And so we have things that were reminiscent of what we were doing are use case diagrams that we can have a passenger and a driver who are more specific cases of vehicle occupants that are associated with the automobile. You can have baggage, and so that would be something you can put a bag in an automobile domain. You have the actual vehicle itself, and it has certain ratings that can go so fast, it weighs so much. You can then, if we wanted to, we could divide it out here. We can have the physical environment, and so we can be thinking in terms of the road. You can be thinking in terms of the atmosphere or other external entities. It has to navigate an intersection or obstacles or stuff like that. So that would be one of the ways that you can be seeing some of this being laid out. You can actually label these things. And so here we can see that this relationship is called R. For atmosphere, it's just labeled ATM. For baggage, it's labeled bag. These are also some things that you can be doing. This is another example that probably what I would say would be a good way for you to be thinking about how to organize your block diagram for your first block definition diagram is label it by subsystems, and you can be thinking of the body, the chassis, the interior, the powertrain, the braking assembly. And then here in the powertrain, we get more details. We can go down multiple layers here. And here we have a trade. We can have an option for a 4-cylinder car or a 6-cylinder car. And so here we have a different type of arrow. So those would be some possibilities that might be useful that you might want to be capturing with a block definition diagram. So what are the purpose? It's depicting relationship between blocks. It can have a composite association or a generalization. We got a chance to see some of those details with some of these different funky arrows, and there's some different types. We can depict structural features of the block. We can have part properties, value properties. We can have ports. We're going to be getting into these with a couple of the other diagram types, like the internal block diagram. You also can do depiction of behavioral characteristics of blocks, operations. All of these are things that are within the realm of what can be done. So here we can be seeing a composite association in the lecture notes that I showed. I showed this surveillance system. This is a block definition diagram that's trying to address some of those same things. This is for a camera. For a camera, it needs to have protective housing, so it's going to be operating outdoors. It needs to have a mount assembly. It needs to have the electronic assemblies. So the actual imager, and then you have the camera module itself, the housing and the electronic assemblies fit within it. And then we could break out for the model assembly. It's not just going to be fixed, it's going to be able to move, pan, and tilt. Those are going to be all of the things that would be within the possibilities of what you could be doing with that surveillance system. So you can have generalization, and so this is this arrow that the head is not filled in. And so the block definition diagram can be used to depict generalization and specialization features. It facilitates reuse of the specialized blocks, which are subclasses. And so here we have the structure of the camera. So you can either have a wired camera or a wireless camera. And so these are two possible implementation options. The specialized class, the subclass inherits, that is, reuses the features of the generalized class and adds its own features. So and so depicted with a closed arrow pointing towards a generalized block. We're not going to get into this, at least initially, with our block diagrams. You're welcome to give that a shot, but trying to give you the general sense of everything that you can have with this. The value properties, it's used to model quantifiable block characteristics or attributes. It's based on value types, which describe the value for quantities. It's listed in compartments using the following syntax, the value property name. So here we can see the aperture, and then we can have the value type name. And so here we can have that. This would be for a listening. We can also have value properties. And so you can have default values. You can also define a probability distribution for their values. You can also have ports. And so this is where you start to get into, you have a specific interface. You're starting to get into the details of describing more specifics about interfaces. And the internal block diagram is one area where this is comes to be a lot more. And so these are examples of different types of interfaces. And so you have an input port with an arrow going into the system, an output port where it's going out. You can have an input and output port where you have arrows going in both directions. That would be possible as well. You can have some other types of things. You can have standardized ports, some interface ports. And so you can have like this ball and a socket where they fit together. And so these are some of those nomenclature things that start to show up here. So thus you can see with a monitoring station, we can see that there's a lot of things that are associated, various type of characteristics. And so here we can have operations. And so the way it's shown here is it's like a method. And so this is trying to leverage some of the unified modeling language notation. And so create route. And so it's like a method. And so these are verbs, test camera, verify logic, check capacity, pan the camera, tilt the camera. These are within the possibility of what you could be doing with the block definition diagrams as well. So this is the level for your first block definition diagram that would be perfectly acceptable, and I'm going to show you one. So this would be for a parking garage, and you have elements that are associated with it, a driver. So you could just put this as a box as well, or you could import a stick man visual paradigms. I don't think you can directly put it into a block definition diagram, but if you define a stick man, you can actually drag it in, and I can show you that. So you can have a vehicle, the parking garage system, and here you have a credit card authority. So these would be things that are part of this parking garage system that are the top level components that we wanted to highlight. That would be an example. Here you can see that now it's getting more complicated. So what I would like to have people start out with is a high level block definition diagram like this. And let's start to go into more details where we can have at least another layer that we start to put in. So a control unit has a processor, display unit, a magnetic stripe reader, printer. Those would be things for the gate assembly. There's a gate itself, the sensors, the gate motor. Those would be some details that we would be capturing. Here you can be seeing it for a magnetic reader. So there would be two possibilities. It could actually be, you can have a paper ticket that is meant to read that would be for one use. Or it could also have a credit card reader that you're trying to pay for it. And so we could have a couple different scenarios that we would need to be making sure that we're able to manage. So just a summary, a block is the basic structure of element used to model the system structure. The block definition diagrams are used to depict definitions of blocks, how blocks relate to each other. Block structural characteristics include part properties, part value properties, and ports. So this is the next layer of detail, and we can show relatedness to other things that we're developing. The block functional characteristics include operations and receptacles, and we have like this ball and joint type of way that we can show relatedness. And block relationships include associations and generalizations. So let me pause now for that to see any comments or questions on that, or you can just also just give me another thumbs up if you got the general sense of what we had there. Okay, at least a couple. I know that some of this is complicated, and we're going to be continuing to go over this as we go. Right, let me pull up visual paradigms. And let me just do another check. Thumbs up. Can you see my visual paradigms environment here? See it? Okay, good. So this is an example of a block definition diagram. And so let me just start something from scratch. I'll just to, if you guys haven't started one, this will be a way that you can get a chance to see what this is like. So okay, the example that I have been building is based on a CubeSat analogy, and so I'll just do something different. And so whoever puts a thumbs up first, I'll do your project between Abby, Jonathan, Kyle, and Nathaniel. Who would like to have me model yours? Any takers? Okay, Nathaniel. Okay, so this is going to be a missile silo. If I can spell it right. So something like that. I probably haven't spelled it right. And so this is the first block. And so what would be some of the elements, the key elements that I would want to have? And so a missile. So that would be something. The the door. Let's assume that it's built in a subterranean fashion, and so there's a minimal thing that is protruding from the ground. You would need to have the silo itself. And I'll just keep it simple, just have one mortar block and call it the control. So here we have 5 blocks, and so we want to do those connections. I find it's a little bit easier just to do it this way. Do that right click. Turns out if you don't put a name, it'll just automatically create a new block. Try this. Not sure what I did wrong. I picked the wrong one. Oh, okay. I picked the wrong here. This is actually called an interface block, and that's the reason why it's giving me an issue. So I want to delete that. Okay, let's give me some issues here. Okay, so maybe this will take some of the mystique out a little bit. You can see what happens by what I've done. I've created 4 subblocks here, and it actually lists them as parts. If I was to wanted to associate something else from my model, I would start to get some of these characteristics that we saw with these different lines that started to show up here and these different fields. Here we can see that. Here we can see some sub, well, this is, yeah, this one I think would be good. So here we see parts, and so we have all these different parts, and then we have values, flow ports, standard ports. Those are some things. And those are just some examples of the possibilities of what can actually show up here. So if anybody had, if some of you haven't finished your block definition diagram for the assignment, start with something like this. And so let me just do a quick round the room. Did you guys follow what I got there? Okay. Well, I'm going to switch over to a couple other ones to make some more points here. So this is still within visual paradigms. And so this is something that I've been working on for several classes. And so we can see there's a lot more information here. I have here for the overall, the ECS CubeSat mission, there's the parts. And so we have the CubeSat, we have the ground station, we have the mission operations. And for Kyle, this would be like at the top level that you would want to be developed. And since you wanted to be focusing on the power subsystem, you would want to be having more blocks that are associated with it. There's also here a requirement. It's allocated to a requirement associated with the APU SAT-1 mission. So this is something that also can show up here. Here I see something called a reference. And so this is a reference to the orbit. And so I had something else that's defined there. This one also has references. And so when you start to develop a one diagram, and so if I was to come back to this actually before this class, I decided to make these a little bit larger because some of this were hidden. So it was like this. And so, there was things that because, so literally when you're using visual paradigms, you're creating a database and there's a relatedness of components and elements that you're generating and you're constantly adding to it. And so that's one of the things that is kind of a cool feature that's taking place. So this is the first version, a general version to give you a canvas. And this is where it can start to be fleshing out in more details. And so say for Kyle, with him working on a satellite, and so you have the CubeSat mission. Here we can be thinking about we have the CubeSat, and then within the CubeSat, there's a payload. There's also the bus, and part of the bus would be the power. And so we have multiple layers that are starting to come together when we start to flesh out some of these details. And you can see that this other one that I showed is a nice top level, and this may be adequate, but then when you start to flesh out more of your design, you're going to start to get into ones that are like this. So let me pause for a second to see if there's any thoughts or questions on that. You guys following what I have there? Okay. Just checking, Kyle, is that making sense? You following along what I've got?
Yeah.
Okay. I think that's everyone. Just wanted to make sure. So basically with tools like this, the best way to do it is to learn by doing. And so this is where system engineering gets into this. It's art and science. So some of it can be a creative endeavor. And so I just wanted to give you some context. System engineering, you have to think hard. You have to be thinking through the details, but you also have to not get lost in the details. And so seeing the larger picture. So this is some stuff that I showed you last time, thinking in terms of some of the requirements. So I'm not going to go over that again. But then here is an example for this forest fire detection system that Freudenthal is using here. This is something that is kind of like what I was showing in the visual paradigms example, giving a relatively simple diagram and then adding more things to it. So this is the mission context. And so there's a lot of things that are here. There's a fire department is involved. There is the space environment. There's a launch environment. There's you're monitoring the Earth, and so that's actually brought in as a separate element. And then they talk about this mission enterprise, and so they flesh it out like that. And so this was a context that was beneficial for them to capture. They even call out GPS as being a key external system that they're going to be depending on. Well, here's something that they also got into more specifics. They started to look at the characteristics of the satellite itself, the mass, the cost, the reliability, the power. And so this is one of the things that Kyle is working on. And so just to give you another context there, this is a requirements document, but this almost kind of looks in a sense like the structure of a block definition diagram. So we have these different environments, performance, physical characteristics, the quality characteristics, the launch things that need to be specified here. And this is now showing you what in this Cameo system modeler, what it would look like, the thing that I showed you with the visual paradigm, but this is a more detailed view. And so this is trying to give the spacecraft physical decomposition. And so this is where now we're not just talking about functional. So functional, maybe just having these headers, but the physical is now we start to get into these specific, this next level of details. And so we're going to have a communication subsystem. Well, what are we going to do in that communication systems? What data rate? So there's going to be a high data rate, a low data rate. Those would be things. There's going to be an antenna control unit associated with it. Here you can see that the power subsystem, so these are the things that Kyle is wanting to focus on. There needs to be a battery, and so you need to define what, how big of a battery. You need to define the solar panels. How many solar panel arrays are you going to be using? How are you going to condition that power so it comes in, say, 28 volts, and you have users that need 5 volts, 12 volts, and 28 volts. And so you're going to have this way of conditioning that power, making sure there's no ripple on that power going out. There's a lot of details that we're just barely getting a chance to touch the surface of what we're thinking about here. And this one kind of blows your mind, but this is actually expanding what we had in that other diagram and getting into a lot more details here. And so maybe it won't be easy to read, but I'll just try and pan out just to give you an idea of this whole totality of what's there. This just gives you an idea of what you can start to generate with these different diagrams, and you can get more and more specifics, more and more meat that you're applying to what you're trying to accomplish. Since Kyle is interested in the power subsystem, this is yet more details that talk about that. Here you're not only talking about solar arrays, but having it gimbaled, so it's actually going to have actuators to keep the solar panels facing the sun. That would be something that is yet another complexity that you have here. You have some more details about these subsystems that would be associated with this. And so here, there's the possibility that you can actually have this other term. I haven't tried this in visual paradigms. You can actually have another highlighter that you're calling it a hardware. So here you can have a subsystem. And so in visual paradigms, what you can do, you have this possibility that you can have different types of blocks. You can have a block. You go over here and see if I can get it to pop up. You can have a domain block, a system block, an external block. And so instead of saying block, it would say system block if I was to put one there. That's a possibility. So any comments or questions on that? Okay, so how many diagrams do you want us to submit? I would say at least 2. And so having a high level context diagram, the things that you would start out with a customer or a stakeholder. So this would be like this first one that I had. And then having a one that's more detailed like this. And let's say there's a specific subsystem that you're prioritizing. So say for Kyle, it could be something like this, where you're trying to focus on the power subsystem. You can see like the other diagram here, when this gets so busy, it's hard to see it all. And so what you start to do is you snip it. And so here I'm just going to be focusing on this power subsystem. And you can just have that fleshed out in more details on a separate block definition diagram. Does that help, Abby?
Yeah, thank
Okay. Any other comments or questions? Okay, I think that's a good breaking point. Look forward to continue to walk through this material and give you a better sense of what system engineering is all about, and giving you a chance to have an effective on-the-job training of you building a project as we go. So we'll leave it at that, and the Lord bless you all. Have a wonderful rest of your day. God bless.
Thank you, President.
Thank you.
Thank you.
Thanks. That's a funny effect.